This is a video from section 4.2 in linear algebra. Let's take a look at this example. Let S equal the set containing the vectors v1, v2 through vn be a basis for a vector space V. Show that the span of S is a subspace of V. First, we want to show that the span of S is non-empty. And I want you to notice 0 is equal to 0v1 plus 0v2 plus all the way through until 0vn. And notice how I wrote the 0 vector as a linear combination of the vectors in S. So this belongs to the span of S. And so therefore, the 0 vector belongs to the span of S. And so therefore, the span of S is non-empty. Okay, now, let vectors V and W belong to the span of S and K be a scalar. So we want to show that V plus W belongs to the span of S and KV, right? So if I add two vectors, they belong to the span. If I take a scalar multiple of a vector, that also belongs to the span of S. Okay. Since V and W belong to the span of S, then there exists scalars C1, C2 through Cn such that I can express V, right, as C1V1 plus C2V2 plus CNVN, right? That's what that means to be in the span. Also, there exists scalars K1 through Kn such that I can say W is equal to K1 V1 plus K2 V2 all the way through until Kn Vn. Okay. Now we're set. So we wrote V as a linear combination of the vectors in S. We wrote W as a linear combination of the vectors in S. Now, what I want to do is I want to look at V plus W, this vector. Now, remember, V is C1V1 plus C2V2 all the way through, right? So I'm going to write that first. C1V1 plus C2V2 plus all the way through until CNVN. And then I'm going to go plus K1V1, right? This is W, plus K2V2 plus all the way through until KNVN. Is that okay? Right? Now, I'm going to collect the terms that involve the v1 vector, the terms that involve the v2 vector, etc. In other words, I'm going to rewrite this as c1v1 plus k1v1 plus c2v2 plus k2v2 plus all the way through until cnvn plus knvn. And then I got one more step here. This can be written, remember we live in a vector space. So one of the axioms tells us we can write this as c1 plus k1 times v1 plus c2 plus k2 times v2 all the way through until cn plus kn times vn. And this belongs, so notice, if I look at just this, c1 plus k1 v1 plus c2 plus k2 v2 all the way through until cn plus kn vn, this belongs to the span of S. And so that implies v plus w belongs to the span of S. So v plus w must be written in terms of that last line ultimately, right? It is not enough to say that if you just look at the first line, that is not enough to show that that sum belongs to the span. Okay? It has to be written this way. Now, if I look at kv, this is k times c1 v1 plus c2 v2 plus all the way through until cn vn, right? Distribute the k. So this is k times c1 v1 plus k times c2 v2 plus all the way through until k times cn vn. But this is kc1 v1, right? One of the axioms allows us to do that. Okay, because we're in a vector space. Plus kc2 v2 plus all the way through until kcn vn. And that belongs to the span of S. Because notice, we wrote kv as a linear combination of the vectors in S. Remember, kc1, kc2 through kcn, those are all scalars. And so, therefore, kv belongs to the span of S. And we can say the span of S is closed under vector addition and scalar multiplication. And so that implies the span of S is a subspace of B. And that'll do it for this video. For section, this is a subspace example, so this is really from section 4.2, although there's a few concepts from other sections. So, All right. Thank you very much.